What's up, everybody? This is Tech G back with another video. And in this video, I'm going to be explaining to you exactly what the routing information protocol is. So let's get into it. If you're just getting into networking, the idea of routers talking to each other might sound a little weird, but believe it or not, that's exactly what happens. And one of the oldest ways they do this is through something called RIP, which is short for Routing Information Protocol. So we're going to break this down in a way that's easy to follow. So whether you're a student preparing for the CompTIA Network Plus, a curious techie, or someone diving headfirst into IT, this video is going to walk you through what RIP is, how it works, and why it's still relevant, even if just barely by today's standards. Before we jump into RIP, let's start with a quick pit stop. Exactly what is an interior gateway protocol? Routers, they need a way to figure out the best path to send packets from one network to another. That's where routing protocols come in. They let routers share information about network paths, kind of like how drivers use GPS or traffic apps to find the latest way home. Now, there are two broad types of routing protocols. The first one is called an interior gateway protocol, and these are used for routing within a single autonomous system. And an AS, this is just a fancy way of saying a network or group of networks under a single administrative domain like a company or a university. And then you have what is called an exterior gateway protocol. And these are used to route between autonomous systems. And the most famous example is called the Border Gateway Protocol, which helps route traffic on the internet. So RIP, this is an IGP. It helps routers within the same organization or network share routing info and build routing tables. All right, next let's talk about the actual routing information protocol. So RIP, this is one of the oldest routing protocols around. It's been around since the early days of TCP/IP networks and was first standardized in RFC 1058 back in 1988. And that's ancient according to tech years. So what does RIP actually do? Well, at its core, RIP, it shares information about which networks are reachable. It measures how far away these networks are using a simple metric called a hop count, and it chooses the route with the least number of hops between point A and point B. And all this sounds simple, right? And maybe it's a little too simple, but we're going to get into the downside of all of this later on. All right, so let's walk through the basics of how RIP works at a real world network. So we have what are called RIP enabled routers that talk to each other. So every 30 seconds, routers using RIP, they send out their entire routing tables to neighboring routers. This is called a routing update. And each entry in the table includes the destination network and the number of hops it took to get there. So imagine router A saying something like, hey, router B, I can get the network 10.0.0.0 in 2 hops. Router B then listens and updates its own table if that route is better than what it already has, and then passes that information along in the next update. Then we have what is called a hop count. So RIP doesn't care about bandwidth, delay, or reliability. It only looks at how many routers or hops a packet must pass through to reach its destination. And the number of hops allowed in RIP is 15. Anything more than that is considered unreachable. So if network X is 16 hops away, RIP won't even try to communicate with it. And then also RIP uses timers to keep everything fresh. So RIP is built on timers, and here are some of the key ones. You have what is called an update timer, and that is 30 seconds long. And this is when routers send out routing updates. You have what is called an invalid timer, and this is 180 seconds long. And this is if a router doesn't hear about a route in 180 seconds, it marks it as invalid. And you also have what is called a hold down timer. This helps stabilize the network by preventing routers from accepting potentially bad updates for a certain period. Then you have what is called a flush timer, and this is 240 seconds. And this is how long a route will stay in the table before being removed. All right, so like most tech, RIP has evolved over the years, and there are 2 main versions that you should know about. So you have RIP version 1, which is the original version. And this came out in 1988. It's simple, but it has some big limitations. First limitation is the classful routing only. So it does not send subnet mask information. So it assumes only default masks. There is no support for VLSM, or variable length subnet masking, and this limits your ability to design flexible networks. Then there's broadcast updates. So we use this broadcast to share updates, which can be annoying on busy networks. And there is no authentication, so anyone can send routing updates, and that's a big security hole. Then you have RIP version 2. This was introduced in 1994, and it fixed a lot of these earlier problems. So now it has classless routing, and this supports VLSM and subnet masks. There's also multicast updates. So we use this multicast instead of broadcast, which reduces unnecessary traffic. And then there's authentication support. So you can require routers to authenticate routing updates, although it's just basic password-based authentication. So if you're using RIP today, which is not super common, but it is possible, you're almost certainly using RIP version 2. All right, next let's go over an example of RIP in action. So let's say you got 3 routers. You got router A, which is connected to 192.169.1.0/24, router B, which is connected to 192.168.2.0/24, and router C, which is connected to 192.168.3.0/24. All 3 routers are running RIP version 2 and are directly connected in a triangle. Now, each router will learn about its directly connected networks. They will also send its routing table to neighbors every 30 seconds, and they will update their table when they hear about new routes with hop counts. Eventually, all routers, they learn about all 3 networks, and each knows the best or shortest hop path to reach each subnetwork. All right, so let's talk about some of the benefits of RIP. So, why did people use RIP for so long? And why do some still use it in labs or very small networks? So, here's what Routing Information Protocol gets right. It's easy to configure. So, RIP is dead simple. You can get it running in just a few lines of configuration. It's often used in teaching environments because it helps newbies understand routing without diving into complex metrics. It also works in small networks. So if your network has 5 to 10 routers and minimal change, RIP can still get the job done. It's lightweight and doesn't need much memory or processing power. And it's supported almost everywhere. Because it's old, RIP is supported on just about every router, even the older devices. Now let's talk about the not so great stuff. And one of the drawbacks here is its hop count, which is a poor metric. So RIP chooses routes based solely on hop count and not on quality. So a 2-hop route over slow dial-up links, this might be chosen over a 3-hop route using fiber, which is not ideal. Also, when it comes to scalability, RIP is terrible. So with a 15-hop limit, RIP just does not scale. And once your network gets large or complex, it will start to fall apart. Also, the convergence is slow. So when there's a network change like a failed router, RIP can take minutes to converge. And that's the time it takes for all routers to agree on the new best paths. Other protocols like OSPF and EIGRP, they do this in seconds. Also, RIP is vulnerable to routing loops. So without careful configuration, RIP can suffer from routing loops, and this is where routers send packets in circles. And techniques like split horizon, route poisoning, and hold down timers, they can help, but they're more like band-aids instead of real fixes. Now, speaking of routing loops, let's go over a few of RIP's built-in defenses. The first is called split horizon. So this is where you don't tell your neighbor about a route that you learned from them. It's like saying, hey, I can get to that place through you, which would create a loop. Another defense is route poisoning. So if a router detects that a route is down, it advertises it with a hop count of 16, which means it's unreachable. And this tells everyone to stop using that route immediately. And then we have what are called hold down timers. So when a route is declared down, routers won't accept new information about it for a set amount of time, even if someone claims it's back. And this helps prevent bouncing and flapping routes. So exactly where is RIP being used today? So it's not being used in large enterprise networks anymore. That job now belongs to OSPF, EIGRP, and BGP. But RIP is still found in educational environments because it's easy to teach and visualize. You'll find it in legacy networks with some older devices or embedded systems that still use RIP. And you'll find it in simple test labs because it's great for quick router simulations or packet tracer lab exercises. And here is a screenshot of RIP going up against other IGPs or interior gateway protocols, such as OSPF and EIGRP. So you can take a picture of that if you want to, but I'm just going to move on with the presentation. All right, so that brings us to the question, should you still learn RIP? Absolutely. So even if you never use it in production, understanding RIP is foundational for learning how dynamic routing protocols work. It sets the stage for understanding OSPF and EIGRP, which are more complex, but they use similar concepts. Plus, if you're studying for your CompTIA Network Plus or your Cisco CCNA or some other certification, you'll definitely encounter RIP in the curriculum. And here's a quick RIP configuration. So if you're using Cisco routers, here's a quick and dirty RIP configuration to get you started. So the commands are router RIP version 2. You identify the first network, you identify the second network. And that's pretty much it. RIP is up and running. And every 30 seconds, the router will send updates to its neighbors. Now, to wrap all this up, The routing information protocol, it may be outdated in many real world environments, but there's still a lot of value in learning how it works. So think of it as the quote unquote training wheels of dynamic routing. It teaches you about routing tables, updates, metrics, convergence, and loop prevention, all of which are crucial topics in networking. So the next time you see RIP mentioned in a lab or a test question, don't roll your eyes. Just give it a nod of respect because it is what helped build the internet that we use today.